We are going to describe the motion using several different coordinate systems. As you know, when the object kind of moved along the curved path, because curved path is general motions that include like a straight motion sometimes. So we used rectilinear coordinate system. Okay? So when you describe this motion, sometimes you use this rectilinear coordinate system, which means you just set x and y, and then just think about the position vector that has x and y components and describe motion along with respect to xy coordinate system. And then sometimes it's convenient to describe your motions using normal and tangential components. So in a case, you know that the velocity is always tangent to the path, and then there might be tangential acceleration and normal accelerations. So sometimes we just describe your velocity acceleration along the normal and tangential components. Okay. And then right now I want to explain we have another way to describe motion using polar coordinate system. Polar coordinate system. So what is a polar coordinate system? So you already learned how to describe or locate your position using polar coordinate system. So in order to locate your position of any object, okay? So this is A. So your A position-wise is X, A, and Y, A, right? So your A position is X, A, and X, Y, A. So this is the rectilinear coordinate system. But we can use the polar coordinate system. Polar coordinate system has two units, so which means what is your R and what is your theta. Okay, so let me just re-explain about the polar coordinates. So in the polar coordinate system, instead of using x and y, we can just use r and theta. So in here, we have the positions. So instead of using xa and ya to locate this position, we simply use r and theta. Right? So here, so how do you represent the position? I simply use r and theta. How about here? How do you represent this position? I simply use my r and this theta. So using the r and theta, that's the polar coordinate system. So instead of using x and y coordinates. Okay, then if you use the polar coordinate system, then forget about the x and y. Okay, forget about the x and y. So this is polar. So if you just describe the motion using the polar, so this is my r and theta, then we can define the unit vector along this r vector. So this is r, and if you just extend this kind of line, so along this line, this is the unit vector of the radial direction. So this is radial direction. And once you define the radial direction of r, perpendicular to the radial direction is called transverse direction. Transverse directions, that's the directions of changing the theta. Okay. So polar coordinate system, we define the two unit vector, radial direction and transverse direction. Okay. The radial direction is the same as your r vector. Okay, then what's the position? What's the position of A? Position A. So I just represent position of A with using the R vector. So with respect to O here is equal to my R and UR, right? So my position A is simply my R, which is magnitude from here to here. That's the distance of my object from O, and UR vector. So this is unit vector. How about the velocity? How about the velocity? So velocity is just time derivatives, right? So dr a dt, that's the velocity. So I need to take a time derivatives dr dt over dr ur, and plus r dur over dt. So this is just the r dot. So if the radius r is kind of changing as a function of time, we can simply define the dr over dt, and this is ur, and this is r, the length of the r at a given time, and dur over dt. So did you remember that when we take a derivatives of the I unit vector before on a rectangular coordinate system, this one will be 0 because I direction is always pointing to the x, and also the magnitude is always 1, so that's why this one is 0. But this one is not 0 because UR. So UR unit vector, the magnitude is 1, but as this one is moved, the UR, the direction is always changing. So actually the dUR over dt is not 0. So we need to figure out what dUR over dt. So that's a little bit tricky. So let's try to find dUR over dt. So let me just make this one a little bit better so that we can use that. So just the example, so let's say we have this kind of path, and then this is just imagine that the particle move along this position to here. Okay, so let's say this is A position and A prime position. Okay, and this time and this time let's say our origin is about here. Okay, so which means this is my R. Okay, so this is my R and this is my R, and then this is my UR direction. Okay, so let me just use another color. And then my perpendicular one is u theta at this time. And then after the particle move a little bit, then this is my UR direction, and perpendicular UR is u theta. Okay, I just use a two different color code. Then let's try to align these two vector on here. So this is a UR and this is u theta. Okay. And then if I align the center together, so this is UR and this is u theta. Okay. Then the magnitude of the unit vector is always 1. So maybe I can just imagine that everything is on the center. So this is center and this is unit circle. Okay, and then this is delta theta. Okay. And then because this UR changed the direction to the red UR, so I can think about delta UR. Okay. So delta UR is this one, and likewise this is delta U theta. So this is a change of UR. So delta UR is equal to what? So just imagine that I want to get the length of the arc of this triangle, small triangle. So the length of the arc is radian, the delta theta, times the radius of this length. So this is 1. So that's the magnitude of this length. How about the direction? What's the direction of this delta UR? So if delta theta is very, very small, the direction of this black one is the same as this U theta, right? That's why I just write down this is U theta. So DUR is equal to the magnitude of this length, which is delta theta times 1, and direction is the same as the U theta. Okay? Then I want to find this DUR over DT, right? So DUR over DT means DUR and delta T, and delta T goes to almost 0. That's DUR over DT. So if I just write down this one, so this is a limit, delta T is going to 0, and DUR over DUR is delta theta 1 transverse dt. So this is equal to limit delta theta over delta T and U theta. So what is it? So this delta theta over dt is angular velocity. So this is theta dot U theta. That's the angular velocity, which means when some object is rotating, you can represent the velocity, angular velocity, like 60 RPM, revolution per minute. That's the angular velocity, right? So that's the angular velocity. This is angular velocity. So what's the velocity of A? I want to find this one. So that's why this is okay, R dot UR plus R and theta dot U theta. So my velocity of A can be represented by the rate change of my R, okay, rate change of my R. And then I have another velocity component along the transverse direction, which is R theta dot. So if I just simply make this one, so my velocity of A is a change of R and also R theta. So this is, let's say, maybe, okay, so I can simply represent this is R dot, that's the velocity along the UR, and perpendicular R theta dot. So the velocity of A can be represented by R dot along this R direction and along this perpendicular to the R direction, which is R theta dot. That's the velocity along on the polar coordinate system. Okay, then how about the acceleration? Acceleration of A. Acceleration of A. So let me just take a derivatives of this one again. So I will just use this area here. So let me just erase. So accelerations A. Okay. I want to take a derivatives of my velocity. So I need to take derivatives of RUR r theta dot u theta dt. Okay, so the first I need to do r2 dot ur plus r dot dur over dt. That's my first term. And second term, r dot theta dot u theta plus r theta 2 dot, this is 2 dot u theta, and then r theta dot du theta over dt. So everything is understandable except this one. So how we can get du theta over dt? So just look at this one again. Just look at this one again here. So I want to find the du theta over dt. So likewise, just think about what is a u theta. U theta is the same as delta theta times 1, that's the magnitude. What's the direction? What's the direction of this, the black u theta vector? That's the direction as the same as ur, but the opposite direction at this instant moment. So this is minus ur, right? So this direction is the opposite of ur, and the magnitude of this length is the same as delta theta and 1. So I just write down here. So this is minus delta theta 1 ur. Okay. Then I want to find the du theta over dt. So this is a limit du theta delta t. So this is a limit and minus delta theta 1 dur dt delta t. So this is the same as this one. So this one is minus ur and limit delta theta over dt. So that's the same as minus theta dot ur. Okay. So I just replace with this one. So let me just write down more nicely. So this is r2 dot ur, and then r dot dur over dt is theta dot u theta, okay? And r dot theta dot u theta, r theta 2 dot u theta, and r theta dot du theta over dt is negative theta dot ur. It's a little bit long and complicated, but just collect everything as the same direction. dur. So this is r2 dot, and this is ur minus r theta dot square, and that's it. That's the ur plus. I have two of these ones. 2r dot theta dot plus r theta 2 dot u theta. That's it. So this is the acceleration. Wow, complicated. A little bit, but let me just give you an example how we apply these kind of equations. So this is position of A when you use the polar coordinates, and velocity A represented by this one, and acceleration is this one. Okay. So okay, then let me just give you examples of how we apply this one. But this one is kind of conceptually important, so I hope you understand everything on this one. So let me just do the example, very simple example. Okay. So just remember, remember this one and this one and this one. Okay. So this example. There's a big plate, okay, and this big plate is rotating. So what's the angular velocity? So angular velocity is equal to 0.2 radian per second. So per second, this one is rotating 0.2 radian. Okay. and then this is and some person is on top of the plate, and he's just running out of the center at 0.5 meter per second. Okay, so this person run outward in radial direction from center with the constant this is acceleration, with the constant accelerations 0.5 meter per second square, and this platform rotates at 0.2 radian per second. So let's try to find the radial and transverse component of velocity and acceleration at time is equal to 2. That's the problem. So let's try to find okay, radial and transverse component of velocity and acceleration of this person at time is equal to. So this is, everything is rotating, and on this is rotating, and some person is running out of the center at constant acceleration, which is 0.5 meter per second. So let's try to find the answer. So using this one, okay, we know that this person is running out from the center, which means your R. So this is we use the polar coordinate system, right? So let's say this is your origin, and this is theta. Then this is the R, right? Then this R has the constant velocity. So we know that R2 dot. Okay, R2 dot is the acceleration along this radial directions, which is 0.5. Okay. Let me omit the unit right now. And then our given condition is theta dot is 0.2. Okay. And then the angular velocity is constant, which is 0.2, which means angular acceleration is 0. Which means theta 2 dot should be 0, because the velocity, angular velocity is constant, so which means angular acceleration should be 0. So we want to find the velocity of a person and also accelerations. Okay. So what is the velocity? So velocity is this one, right? So let me just use that this fraction, this equation. So this is r dot ur, r theta dot u theta, and then do we know the distance from here to here right now? So right now this problem set doesn't give us any okay, so we just make another assumptions that when time is equal to 2, the r is 1 meter. Okay, so let's just assume that this, when time is equal to r is 1. Okay, so let's assume that this person starts from the center. So when the time is equal to, the length of the r, okay, is just 1 meter. Okay, so in a case, this one gets simpler. So right now, what is r dot? So we know the accelerations, but we need to know the velocity of r dot. So how do you get the r dot? So we need to integration of your acceleration. So your acceleration is 0.5. So which means your r2 dot is 0.5. Okay. So this is dr dot over dt. So if I want to get the r dot, so I just want to take a derivatives of 0.5 dt and dr dot over this one. So from 0 and then from 0 to t, so 0.5 t is equal to so we are going to look at the time 2, right? So this is time 2, and then this is dr dot, so this is just dr dot, So our dr dot, our r dot is just 1. So which means this is 1 meter per second. Because we know that r2 dot, the acceleration along the radial direction is 0.5. So this person run from the center at the beginning. So if I just integral this one, 0 to 2 seconds, so 0.52, which is r dot. So my r dot is 1 meter per second. So this is 1 ur, and then when time is equal to, the radius is 2 meter, and then angular acceleration is 0.2. So this is a u theta. So that's the velocity. Okay. Velocity. So basically, if I just visualize the velocity, so this is 1. So the velocity is, this is 1 meter per second, and 2.0 is 0.4. So actually, the velocity along the transverse perpendicular this is 0.4. So this is 1 and 0.4. That's the velocity profile. How about the acceleration? So acceleration, I just use this one. Okay, r2 dot. R2 dot is 0.5 minus r is 1 meter, and then r dot is 0.2 square ur, okay, plus, and r dot, we just got the r dot. R dot is 1, 2, 1, and theta dot 0.2 r 2 1, and theta 2 dot. Theta 2 dot is 0. So this, if you just compute this number, then you can get the accelerations along ur and u theta. Okay. So this one looks complicated, but in many cases, especially when the motion has rotational motions, and if the angular acceleration, angular velocity are given to your the problem set, then it's more convenient to use the polar coordinate system and represent your velocity and acceleration along the radial direction and transverse direction. Okay. So if you just do some more practices on the examples in your textbook, you have more better ideas how to apply those kind of equations to different problem sets. So let me just do one more thing, and then I will close this video. So right now we just get the position. Let me just do, this is position, and this is velocity, and this is acceleration. Okay. So let's a little bit simplify this problem. Okay, so right now this is just general polar coordinate system, but just imagine that your particle just move the circular motion. Okay, so circular motion. And if you apply those kind of equations to circular motion, let's see how this one change. So circular motion means the r is always the same, because that's a circular motion, which means r dot and r2 dot will be 0, everything. So the position of A is the same as this one, but in case of circular motion, the velocity of A, okay, velocity of A will be, this one will be 0, right? So that's why this is r theta dot u theta. So what does that mean? What does that mean? So your velocity of A is equal to r and angular velocity. If you know the angular velocity theta dot, then your velocities are theta dot in circular motion. How about the angular acceleration? So I told you that r dot r2 dot will be 0, so this one will be 0, and this one will be 0. So this is r theta dot square u r, and then this is r theta 2 dot u theta. Okay. So if this rotationer has angular acceleration, so the angular velocity is getting faster or getting slower, then we need to account for the theta 2 dots, okay? And then direction is transfer directions along the same as tangential directions. And then this is a normal component of acceleration. So just look at this one. So what's the meaning of the negatives? Which means the acceleration of A pointing to the center, because UR direction is outward, so negative means inward. So acceleration of A has a pointing to the center, which is normal direction. This is normal to the motion, and this tangential. So did you remember that when we talk about the circular motions, the normal component acceleration is v squared over r, right? So let's look at this one. So we know that the v is r theta dot. Okay. So what is r theta dot square? So this is let's say r theta dot square. So I just multiply r and divide by r. So this is r theta dot square over r. So this is a v squared over r. Actually, this is the same as v squared over r, right? So this is minus v squared over r, ur, plus r theta dot u theta. This is 2 dot. So this is normal directional accelerations, and this is tangential component of accelerations if the angular velocities keep changing. So this is final notes. So basically the polar coordinate system include circular motions as well, and in case of circular motions, polar coordinate system can be represented as if we used normal and tangential components.